Namaste to everyone. I welcome you all in my YouTube video channel. Today I will tell you our lecture on zeros, singularities and poles. Lecture number 6, in which I will prove the Riemann theorem and Weierstrass theorem. Now we prove Riemann theorem. Statement of the theorem is: let Z not be an isolated singularity of function of Z, and if function of Z is bounded on some deleted neighborhood of Z naught, then Z naught is a removable singularity. Now we prove this. Given that Z naught is an isolated singularity of function of Z, also given that function of Z is bounded on the deleted neighborhood in Z naught of Z naught. Therefore, modulus of function of Z is less than m. M is a positive number. Let this is number 1. Let modulus of Z minus Z naught equal to R is a circle C on the deleted neighborhood in Z naught of point Z naught. Let this is number 2. Therefore, function of Z is bounded on the circle C. Therefore, we may write function of Z in Laurent series as follow. Function of Z equal to sigma n equal to 0 to infinity an Z minus Z naught whole to the power n plus sigma n equal to 1 to infinity bn Z minus Z naught whole to the power minus n. Let this is number 3, where bn equal to 1 by 2 pi I integration along the circle C Z minus Z naught whole to the power n minus 1 function of Z dz implies that modulus of bn equal to modulus of 1 by 2 pi I integration along the curve C Z minus Z naught whole to the power n minus 1 fz dz. This is less than equal to 1 by 2 pi since modulus of I equal to 1, and here modulus of z minus z naught whole to the power n minus 1, modulus of function of z, modulus of dz. Since modulus of I equal to 1, this is equal to 1 by 2 pi integration along the circle C. This is equal to r to the power n minus 1. Modulus of fz is less than m, and here modulus of dz implies that modulus of bn less than 1 by 2 pi multiply r to the power n minus 1 multiply m integration along the circle C modulus of dz. This is equal to m r to the power n minus 1 by 2 pi, and this integration is 2 pi r. This means circumference of the circle, and this is equal to 2 pi cancel, m r to the power n tends to 0 as r tends to 0. Therefore, bn equal to 0. Let this is number 4. So, in theory, we do not get any term in the principal part of the function fz. So, z naught is a removable singularity. Proved. Now we prove Weierstrass theorem. Statement of the theorem is, let z naught be essential singularity of a function fz, and let L be an arbitrary constant. Then for every epsilon greater than 0 and every neighborhood modulus of z minus z naught is greater than 0 less than rho of point z naught, there exists a point z of this neighborhood such that modulus of fz minus L less than epsilon. In other words, in every arbitrary neighborhood of an essential singularity, there exists a point under bracket and therefore an infinite number of points at which the function differs as little as we please from any previously assigned number. Now we prove this. We shall prove this theorem by the method of contradiction. Therefore, let the theorem is not true. We assume that the theorem is not true. And then if we get contradiction, then our theorem will be proved. Therefore, there exists a number L and deleted neighborhood modulus of z minus z naught is greater than 0, less than rho for every point of which and for arbitrary epsilon greater than 0 modulus of fz minus L greater than epsilon. Here modulus of fz minus L less than epsilon. Here we assume in this place greater than epsilon. Implies that 1 by modulus of fz minus L less than 1 by epsilon implies that modulus of 1 by fz minus L less than 1 by epsilon implies that 1 by fz minus L is bounded in this neighborhood. Therefore, by Riemann's theorem, one by fz minus L has removable singularity at z equal to z naught. Therefore, there will be no term in the principal part of Laurent series of the function 1 by fz minus L. Hence, we may write 1 by fz minus L equal to a naught plus a1 z minus z naught plus a2 z minus z naught square plus dot 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 plus am z minus z naught whole to the power m plus am plus 1 z minus z naught whole to the power m plus 1 plus dot 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 dot. If a naught not equal to 0, then 1 by f in place of z we write here z naught minus L equal to a naught plus here in place of z naught minus z naught 0, all terms are 0, implies that 1 by fz naught minus L equal to a naught, this is not equal to 0. Therefore, 1 by fz minus L is analytic and 1 by fz naught minus L not equal to 0 implies that fz is analytic at z equal to z naught, which gives contradiction because as per statement z naught is an essential singularity of fz. Let this is number 1 and this is number 2. Therefore, our assumption in 1 is wrong. That is, function of z minus L less than epsilon is true. Therefore, theorem is true for this case. Again, let A naught equal to A1 equal to A2 equal to dot equal to AM minus 1 equal to 0. Therefore, from 2 we get 1 by fz minus L equal to am z minus z naught whole to the power m plus am plus 1 z minus z naught whole to the power m plus 1 plus dot and this equal to z minus z naught whole to the power m am plus 1 z minus z naught plus dot. Therefore, 1 by fz minus L has a 0 z naught of order m, implies that fz minus L has a pole at z equal to z naught of order m, implies that fz has a pole at z equal to z naught of order m, which gives again a contradiction, because as per statement z equal to z naught is an essential singularity. Of fz. Therefore, our assumption in 1 modulus of z minus L greater than epsilon is wrong. Therefore, modulus of fz minus L less than epsilon is true. Hence, theorem is proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.